Let's get started using the Python SWAT package on the SAS Viya platform to analyze and process data. The SWAT package enables you to use the Python language to connect to SAS Cloud Analytic Services, or CAS. If you have access to SAS Viya, I encourage you to follow along with me. Your environment might already have all the files used in this demo. However, if you don't see them, please visit our SAS software GitHub page. The SAS Viya Quick Start repository provides the files used in our demonstrations and instructions for loading them in your environment. In our provided training environment, open Google Chrome and select Jupyter Server on the bookmarks bar. If prompted for a password, enter student1 with a capital S. In the file browser, double-click the Python SWAT package notebook. Let's take a look at cell 1. The code loads the packages that will be used in this scenario. The SWAT package is provided by SAS and enables the Python client to connect to and execute commands on the distributed CAS server. Other local Python packages are imported, including pandas, numpy, os, and sys. The pandas max columns option is set, and the versions of Python, SWAT, pandas, and numpy are printed. Select the first cell, then click the Run icon, or press Shift-Enter to execute the code. The next step is to connect to the CAS server. To establish the connection, you provide the hostname, the port number, and authentication. Examine the code under Step 1. A variable named con is defined, and the swat.cas method includes the required arguments to make a connection to the CAS server. Depending on your environment, you might need to use alternate connection information. Select cell 2 and press Shift-Enter to run it. Once the Python client is connected to the CAS server, you can check the type of the con object. Run cell 3. Notice that the output shows that it's a CAS connection object. We'll use this connection object throughout the notebook to submit code to the CAS server to process data. Next, run cell 4 with the About CAS action to validate the connection to CAS and view the current SAS Viya version. The action shows the version of SAS Viya and confirms that there is a working connection to the CAS server from the Python client. With the connection to CAS established, you can explore the available data. On the CAS server, all data is accessed through a CAS lib. Remember that a CAS lib can include data source files saved on disk and tables loaded into memory. Run cell 5 to view all available CAS libs using the CAS lib info action. In the training environment, all CAS libs are path-based. Run cell 6 to use the file info action to list all the available data source files in the samples CAS lib. The results show a variety of files in the samples CAS lib with the .sashdat extension. Run cell 7 to use the file info action to list the files in the CAS user CAS lib. Depending on whether you have completed previous demonstrations in the Quick Start video series, you may have a variety of files in CAS user. Execute cells 8 and 9 to utilize the table info action to view the in-memory tables in the samples and CAS user CAS libs. Again, you may or may not have in-memory tables loaded into these CAS libs. These in-memory tables are also referred to as CAS tables. CAS tables are similar to data frames when using pandas. The main difference is that the CAS tables are distributed among the worker nodes in the CAS server for parallel processing, and traditional data frames are located in memory on the Python client. Next, we'll load new data into memory for further analysis in CAS. We'll work with the home equity.csv file that is available on the SAS documentation webpage. In cell 10, the SWAT package provides the read_csv method to load the home equity.csv file to the CAS server. This method is similar to the pandas read_csv method. The only difference is that the SWAT method loads the data to the CAS server as a CAS table. The CAS out parameter specifies the name of the CAS table and the destination CAS lib. In this example, the home equity table is loaded in the CAS user CAS lib. If the CAS table already exists, it will be replaced. Run the cell. The resulting log indicates that CAS uploaded the file as home equity in the CAS user CAS lib. Cell 11 uses the table info action to list the available tables in CAS user. Run the cell and confirm the home equity CAS table is available. Once the CAS table is in memory in CAS, you need to make a client-side reference to further explore the data. Examine and run the code in cell 12. The variable CAS_TBL stores a reference to the CAS table by using the CAS table method. In the CAS table method, you specify the CAS table name and the CAS lib. Notice that the CAS_TBL variable is a CAS table object, and it simply references the CAS table on the CAS server. After referencing the CAS table, you can begin executing CAS actions or Pandas API methods from the SWAT package to process the data. For example, run cell 13 to execute the table details CAS action. The action returns results to the Python client and shows general information about the CAS table, such as the number of blocks the data is broken into, the modified date, and more. The SWAT package also allows you to use many of the familiar Pandas methods. The Pandas API methods in the SWAT package process the data on the distributed CAS server and return results to the Python client. In cell 14, the head method from the SWAT package is used on the CAS table object to preview the data. The results are stored in the variable df and displayed. Run the cell. The results show that the SWAT head method returns a SAS data frame object to the Python client and displays 5 rows. A SAS data frame object is simply a subclass to a Pandas data frame and lives on the Python client. You can work with the SAS data frame as you would a Pandas data frame using familiar Python packages. Let's continue to explore the CAS table using a variety of CAS actions and Pandas API methods from the SWAT package. Run cell 15. The shape attribute returns the number of rows and columns in the CAS table as a tuple to the Python client. Run cell 16. The column info action returns information about CAS table columns like column names, labels, and formats. If you want to find the count of unique values in a CAS table, you can use the SWAT package value_counts method, which works like its Pandas counterpart. In cell 17, specify CAS_TBL and then the job column followed by the value counts method, and store the results in df. The type and value of df are displayed, followed by a simple plot using Pandas. Run the cell. The CAS server summarizes the data and returns a Pandas series to the Python client. You can then use traditional Pandas to plot the data. This seamless integration enables you to use the power of the distributed CAS server for data processing and use other open-source packages on the summarized data returned to the client. You can also execute SQL on the CAS server. Examine the code in cell 18. First, the fed SQL action set is loaded with the load action set action. Then, to execute an SQL query, use the exec direct action from the fed SQL action set. Within the exec direct action, you use the query parameter and specify the SQL query as a string. In this example, the query is stored in the variable myQuery. This query counts the total number of rows for each distinct value in the reason column using the home equity table in CAS user. The result is stored in the variable CR and then displayed. Run the cell. The action returns the results as a CAS results object, or a Python dictionary, to the Python client. The key is result set, and it holds a SAS data frame. Once the CAS results object is on the client, you can use traditional Python dictionary manipulation techniques to process it. For example, cell 19 specifies the CR CAS results object, or dictionary, and then adds the key result set. This accesses the SAS data frame. With access to the SAS data frame, you can easily work with the results of the query on the Python client. Now let's do a bit of data preparation. Run cell 20 to preview the first 5 rows of the home equity CAS table using the head method. Next, in cell 21, 2 new columns are created using the eval method. The eval method requires SAS assignment statements and functions. The diff column calculates the difference between the value and mort2 columns. Loan_status uses conditional logic to map the values of 0 as paid and all other values as default. Run the cell. Next, run cell 22 to display the value of the updated CAS table object. Notice that the eval method simply adds parameters to the CAS table object, indicating how to calculate the two new columns. This is because the CAS table object is lazily evaluated. That means any time that an action or method is executed on the CAS table object, the two new columns will be dynamically calculated. Run cell 23 to use the params attribute to view the new parameters on the object clearly. Notice that the results show the CAS table object has the name and CASLib parameters referencing the CAS table. It also contains the computed vars and computed vars program parameters, which contain information about how to calculate the columns. To demonstrate the result of the calculated columns, use the head method. Run cell 24. The results show that two new columns, diff and loan_status, were calculated. Lastly, create a new CAS table that contains the calculated columns. In cell 25, execute the copy table action on the CAS TBL CAS table object. Specify the output information for the new CAS table, such as the new table name, home equity _final, and the destination CASLib CAS user. The label option can also be used to add a label to the table. Notice that the results of the copy table action return information about the newly created CAS table. Run cell 26 to run the table info action again. Confirm the results show that the CAS user CASLib now has two available in-memory tables, the original home equity CAS table and the new home equity final CAS table. Notice that the new home equity final table has a custom label and two additional columns. In cell 27, the code references the new home equity final table using the CAS table method and stores it in a variable final_CAS TBL. Then the head method is run on final_CAS TBL to preview the first 5 rows. Run the cell. Notice that the table contains the two newly calculated columns, diff and loan status. Now that the CAS table is prepared, the in-memory version of the data can be saved as a data source file on disk. This is like saving a pandas data frame back to disk using a pandas to_ method. In cell 28, use the Save CAS action to save the CAS table in 3 different file formats: a Parquet file, SAS HDAT file, and CSV file. A loop is used to specify the CAS table reference, final_CAS TBL, and then the save action for each of the file formats listed in Save File Types. Within the save action, name the file home equity _final with the file extension and place the files in CAS user. Run the cell and confirm in the log that all 3 files are saved. Finally, run cell 29 to execute the file info action to view all files in the CAS user CASLib. Verify the new files are listed. By default, when you load a table into memory, the table has session scope. This means that the table is available to only that specific CAS session, and no other user or other SAS Viya application can access that CAS table. Session scope tables are best used for general-purpose programming and typically provide better performance because concurrency locks are not used. Session scope tables are also cleared from memory when you terminate the CAS session, clearing the resources. Global scope tables are available to every SAS Viya application and every user who has access to that CASLib. Global scope tables also persist in memory even when you disconnect from the CAS server. These are best used if you want to share the CAS table with other users and via applications. Run cell 30 to view the available CAS tables in CAS user. Notice that the global column has a 0 for the home equity and home equity _final CAS tables. That indicates that each table is session scope only. Run cell 31 to view available files in CAS user. Notice that there are 3 files available: homeequity_final.parquet, homeequity_final.sashdat, and homeequity_final.csv. In cell 32, use the load table action to load the homeequity_final.parquet server-side file into memory. In the CAS out parameter, name the new CAS table homeequity_final_global and load it to the CAS user CAS libs in-memory space. The promote subparameter promotes the table to global scope. Run the cell and confirm in the results that the table was loaded successfully. Run cell 33 to execute the table info action for CAS user again. Notice that the value in the global column for the homeequity final global table is now 1, indicating that this table is global scope. Global tables can be analyzed in other Viya applications or accessed by other users who have appropriate permissions. Open a new browser tab and select SAS Viya on the bookmarks bar. Select the Applications menu in the upper left corner, then select Explore and Visualize to open SAS Visual Analytics. Select New Report and Add Data. The global in-memory tables we created are available to use to create a report or build a model. Select homeequity, final, global, and click Add. In the data pane, right-click Loan Status and select Explain on Current Page to quickly evaluate which factors are most related to the loan outcome. Let's return to Jupyter Lab. Another great feature of global scope tables is that they enable you to load data into memory for extended periods of time. The code in cell 34 terminates the CAS session, starts a new CAS session, then executes the table info action to view available CAS tables. Run the cell. Notice that the results of the table info action show that the session scope tables were cleared from memory, whereas the homeequity final global table is still available. To remove a global scope table from memory, it must be explicitly dropped. Run cell 35 to drop homeequity final global using the drop table action. The results show that the table was dropped from memory. If you want to delete the data source files that we created in this demonstration, you can use the delete source action. The loop in cell 36 deletes the Parquet, SAS HDAT, and CSV files that were created earlier. Lastly, to conserve resources, you should always terminate the CAS session when finished. Cell 37 terminates the CAS connection by specifying the CAS connection name, con, followed by the terminate method. We've just scratched the surface of what is possible with the SWAT package and the rest of the SAS Viya platform. If you would like to learn more, please visit developer.sas.com/open-source/Python to discover additional resources for SAS and open source integration.